Okay, so let's continue from where we have left last time. So last time we did, I should also share my screen, we did argument principle and Roche's theorem. Argument principle was basically, it was easy, and it was a corollary to the residue theorem. It was a corollary to the residue theorem, and we would have done it first for a holomorphic function, and then we observed that the same proof goes through for a meromorphic function also. This is a point where maybe I was a bit confused in between, and we got it clarified in the class. So any meromorphic function also it goes through, and so you will basically we have proved that a certain integral, right? Integral of the logarithmic derivative, integral of f prime by f, appropriately normalized as number of zeros minus the number of poles. I mean, we assume that the index is either 0 or 1, etc. Right? So this is what the argument principle said. And as a corollary, we proved the Roche's theorem. So let's go to the slides. I hope it's visible. Yeah. So today's lecture 10, and today we will discuss a little bit more on Roche's theorem. That will be at the end, and we will discuss Lorentz series, which also you must have seen already. But since we are doing everything anyway, we'll quickly go through that. Okay, so that's all that we will do today. So last class we discussed the argument principle and Roche's theorem, and argument principle we already recalled. So 1 by 2 pi I integral of f prime by f over gamma. This is number of zeros minus number of poles, quote unquote, inside gamma. So what we mean by this is we are considering the set of points where the index is set of points in omega. Gamma is homologous to 0, so outside omega index is 0, and inside omega we assume we assume that the index is either 0 or 1. If we don't assume that, the formula will have indices also, but let's assume this, and then we are saying that the number of zeros in the set of points where the index is 1 is this integral, or if it's a meromorphic function, number of zeros minus the number of poles in a set where the index is actually 1 is given by this integral. And Roche's theorem was a corollary because the way we did it, we showed that if f and g are holomorphic functions, then we composed with gamma. So you got these two curves, f composed with gamma and g composed with gamma. And argument principle can be restated as saying number of zeros is same as the index of the curve f composed gamma at the point 0. So in order to show that number of zeros is the same for f and g, we need to show that the index of 0 for f composed gamma is same as index of 0 for g composed gamma, and this we achieved by showing that these two curves f composed gamma and g composed gamma are homotopic in a domain that does not contain 0. So this was a proof of Roche's theorem. Okay, so let's continue. Today we will first discuss the Lorentz series, and then we will come back to see Roche's theorem once again and see a few more applications. And as usual, in the discussion session at the end, we will discuss whatever questions you may have. Okay, so not much today. So Lorentz series, you have seen this already, but quickly. So what is given to us is an annulus. You know what an annulus is. So we will take an annulus centered around 0. Everything goes through for any point A. So you will take two concentric circles centered at 0 and the region in between, open annulus. Okay, so this is all Z such that R1 strictly less than mod Z strictly less than R2. And we want to show that F can be expanded as a series. This is not quite power series because there are also negative coefficients, negative term. Okay, so we can expand it around 0 like this. At any point A, it would be Cn Z minus A power n. And also the convergence is the best kind of convergence. It's both absolute and uniform, where on compact subsets. Okay, as in the case of power series also. So this is what we will do first, and this also follows from Cauchy's theorem. So consider two concentric circles inside the annulus. Let's say gamma 1t is, so I'm taking inside the annulus, so let epsilon be slightly positive, and you take a circle centered around 0 with radius r1 plus epsilon, so that's inside the annulus. Also radius r2 minus epsilon, so that's also inside the annulus. A0 T is between 0 and 2 pi. So two positively oriented circles, concentric circles, gamma 1 and gamma 2, and we are going to argue with this cycle gamma 2 minus gamma 1. So the outer circle is oriented positively and the inner circle is oriented negatively. So consider this cycle and notice that both gamma 2 and gamma 1 uh, they are homologous, right? If something is outside the outer circle, of course, the index is 0 for both of those. And if something is inside the inner circle, then the index is 1 for both of those. So they are homologous. In other words, gamma 2 minus gamma 1 is homologous to 0 in A. If you take any point outside A, the index of gamma 2 minus gamma 1 at that point is 0. And therefore, we can apply Cauchy's theorem. So Cauchy's theorem would say that Fz is 1 by 2 pi I integral of Fw by W minus Z dW, where the integral is over this cycle gamma 2 minus gamma 1. So this is the meaning of that statement, right? So we have Cauchy's theorem. And this I'm going to write as F2 plus F1, where F2 is the first function, 1 by 2 pi I integral gamma 2 this thing, and F1 is minus 1 by 2 pi I integral gamma 1 this thing. Okay. And we are going to show that F2 and F1 are nice holomorphic functions in certain regions. Yeah. So let's see F2 first. We have seen this already, but recalling. Note that quite some time back, in fact, in lecture 2, I checked that. We showed that F2 is representable by power series. So what was the main idea? So representable by power series and therefore holomorphic. And where do you get holomorphicity? F2 is integral over the circle of radius R2 minus epsilon. So throughout the disk D0 R2 minus epsilon, you will get holomorphicity. In fact, throughout this, we are going to expand this as a power series. That's what that proof would tell us. So we'll quickly recall. And therefore also in D0 R2, because you can take epsilon smaller and smaller. So you are getting holomorphicity in this disk. So remember that the trick was geometric series. So basically 1 by W minus Z, divide by W also. This is same as 1 by 1 minus Z by W. And you will expand it as geometric series. For any Z in D0 R2 minus epsilon, mod Z is strictly less than R2 minus epsilon, whereas mod W is on the boundary. You're integrating on the boundary. So mod W is R2 minus epsilon, mod Z is strictly less than that. Therefore, mod of Z by W is less than 1, strictly less than 1. So this has geometric series expansion, and that's what we used. And therefore, this you will expand as geometric series, and therefore what will you get? 1 by W minus Z you will substitute, and you will get summation Z by W power n by W. So summation Z power n by W power n plus 1, and the rest comes from interchanging the integral and the sum. Right? Here you will have a sum and you are integrating that sum. An integral I will put inside the sum because of uniform convergence. So uniform convergence of what? Uniform convergence of the series of functions summation z by w power n. And then you will get it like this. So these will be the coefficients and this is a power series. And this expansion is valid throughout this. Okay, so interchanging the sum and the integral was justified due to uniform convergence of this. So summation z by w power n as a function of w for a fixed set. This as a function of w is uniformly convergent. You fix a z and argue with that z. Okay, as a function of w for a fixed z, and this was because if you name this function g and w, you want to say that summation g and w is absolutely and uniformly convergent, and that is true because modulus of g and w is less than or equal to this power n, and this number is strictly less than 1. Therefore, sum of this is absolutely and uniformly convergent, and therefore sum of this as a function of w is absolutely and uniformly convergent. Okay, so this was the proof. So this is taking care of F2. So coming back here, you wrote this by Cauchy's theorem, you wrote this. This is Cauchy's theorem applied to the cycle gamma 2 minus gamma 1. The integral of a gamma 2 you are calling F2, minus of the integral over gamma 1 you are calling F1. And what we just observed is, we recalled from what we have done long back and we read the proof, and what we observed is F2 is holomorphic throughout D0 R2. R2 is the outer circle. So inside that region, F2 is holomorphic. Now let's analyze F1. F1 is also holomorphic, but where? So same proof. So the same analysis, we can do a similar analysis on F1, which is minus 1 by 2 pi I this time. So if we want to apply the trick, what should be the function which we manipulate using the geometric series? Earlier we manipulated 1 by w minus z. This time we should manipulate minus 1 by w minus z, which is 1 by z minus w. So if you want to get a geometric expansion, this you have to write as 1 minus 1 by 1 minus w by z. So mod w by z should be strictly less than 1. So it's the opposite of what happened in the previous slide. So previous analysis will go through for mod z. So earlier it was mod z less than r2 minus epsilon. Because of this negative sign, analysis goes the other way. I mean, analysis should be on the other part. So it should be outside the circle, outside the disk D0 R1 as epsilon going to 0, right? So outside the circle, outside the disk D0 R1, you are getting analyticity, holomorphicity. So the same analysis goes through mod z bigger than this, and we get F1z is summation n going from 0 to infinity. Power series expansion will be something like this: z power minus of n plus 1, and the integral will be over gamma 1 fw w power n dw, right? This will be 1 by z times 1 by z minus w will have a geometric series expansion. So earlier, a power of w was extra. Here a power of z will be extra, and it will be w by z power n. So w power n will come. So this is what you will get. We can write this using change of variables. So I can write this same thing as, instead of n, I will take minus n. So n going from minus infinity to minus 1, right? N equal to 0 is z power minus 1. N equal to 1 is z power minus 2, etc. So it will be n from minus infinity to minus 1, z power n, and then the change will be w power n will become 1 by w power n plus 1. So this is exactly the previous coefficient, right? It's exactly this coefficient. It's exactly this coefficient. Summation 0 to infinity here. The coefficient of z power n was 1 by 2 pi I integral over gamma to fw by w power n plus 1 dw. It's the same coefficient. It's the same coefficient. 1 by 2 pi I integral, but integral is over gamma 1. Earlier it was over gamma 2, but this is the same coefficient of z power n, but the indices are from minus infinity to minus 1. Okay, so that's it. So that gives you the Lorentz series. Therefore, putting both together, fz is summation c and z power n going from minus infinity to infinity. See, we got this as f2 plus f1, where f2 the coefficient was integral over gamma 2, and f1 the coefficient was integral over gamma 1. But if you take any gamma in between gamma 1 and gamma 2, the integral over gamma and integral over gamma 1 and integral over gamma 2, all these are same, again by Cauchy's theorem. It's all holomorphic in between, therefore the integral will be 0. So the difference integral will be 0, so these integrals are the same. So you can write like this, where the coefficient Cn is 1 by 2 pi I integral fw by w power n plus 1 dw, where over any gamma which is between gamma 1 and gamma 2. So the radius is between R1 and R2. You can take any such circle and integrate over that. That will give you the coefficient. And observe that the series expansion is unique, because if you write it like this, then the coefficient is exactly this integral. And any gamma will give you the same thing. That is clear by Cauchy's theorem. Any gamma in between gamma 1 and gamma 2 will give you the same thing, and that is precisely the coefficient. Anyway, if you have a series expansion like this, then the coefficient is given either by this or by taking derivative, right? Fn 0, nth derivative at 0 by n factorial. Either way, you can see that the expansion is unique. Okay, so small.
Like the derivative, how will the derivative work here? Because we have possibly infinitely many non-zero negative ones, right?
There could be possibly many infinite negative terms like an essential singularity, and therefore, what is your comment?
Then how will the derivative work? Like if we put zero, will the negative ones will cause a problem?
Only the positive terms derivative will work. So the integral, yeah, good. Okay, this is the explanation. Yeah. Uh, yeah, nth derivative for positive terms for power series, we would have concluded that way also. But here we have the uh, integral representation, and that gives you the uniqueness. Yeah, you're right. I said verbally something more, take it back. So the integral representation gives you the uh, uniqueness. Okay, so you should do more exercises than what I give you. I mean, I'm giving very little, but do more exercises. For example, try to write down the Lorentz series expansion of 1 by sine z. So this will have poles at all the zeros of sine z. So all n pi, 0, pi, minus pi, etc. So take in analysis without containing the which does not contain the pole. So this will be holomorphic there, and try to write down the Lorentz series expansion. So you should get a unique Lorentz series expansion. So write it down. You must have done these kind of problems. Can someone does someone remember some of the coefficients? So by writing down, I mean get the first few coefficients. Do you happen to remember some of the coefficients of this function? How many negative terms will be there in the Lorentz series expansion? Right, 1 by z square, etc. How many such terms will be there?
I think only one negative term, right?
Only one negative term, only 1 by z, right?
Yeah. I mean, I'm talking about on the annulus around zero. Yeah.
Right, annulus around 0, yes, yeah. This is, yeah, I did not write this. What I meant is what we discussed. So annulus around 0 is what we are thinking. So 1 by z. And how did you say that, Ariman?
Because as z tends to zero, this function will blow up.
Yeah.
But z by sine z has a limit.
So that is a limit. So it's a simple pole, and simple pole meaning the principal part has only one term. Residue will be exactly that limit, and that is 1. Therefore, it is actually 1 by z. Right? When I said 1 by z, I was not sure whether it was 1, but it is 1 by z because it is this limit, right? So it is 1 by z. And positive terms. Do you happen to remember, Ariman, some of the coefficients?
No.
No, okay, fine. So I looked at it only yesterday. So let me just tell you for the next picture. Okay, so though I looked at it only yesterday, I seem to be forgetting. Yeah, there's no constant term and there is a z coefficient. There's no z square term, there's a z cube coefficient, z cube term, and I think the z term, the coefficient is 1 by 6. So try to work this out, whatever way you do. So z coefficient is 1 by 6 and the z cube coefficient is set by 7 by 360 or something. Okay, so you should do it. And by the way, how will you do it? Will you actually do the integration to get the coefficient?
I was thinking that we could first write sine z
Yeah,
in the denominator as the
yeah,
power series,
yeah.
then take z common out, then we'll have 1 plus something, and
Yes.
then
And, formally
do that.
series. Formally, you can, yeah. So that thing you can write as 1 by 1 minus something and write it as 1 plus that square, etc. and take the see the coefficients. Right. This is formally okay and it can be justified because you know that it has a series expansion and it has to be that. So you will get the coefficients. Okay. So, but from whatever we have discussed, we know that the yeah. Whatever we have discussed, we know that the coefficients are given by integrals. So I was just curious, you can try to write down these integrals, right? Cn is integral over gamma, any gamma will do. So you can take a nice gamma and 1 by 2 pi I integral over gamma fw by w power n plus 1 dw. So at 3, I know that the answer is 7 by 360. And of course, I mean, I can't do this kind of integrals. So I went to Wolfram Alpha and just asked, I don't know how to do all these computations using, I don't know programming at all. But anyway, for people like us, someone else will do it. How many of you know this site or have used this site?
I have used it.
It's quite good, right? I mean, I remember using it long ago, and I think it has become much better now. Omkar, have you used this site, Wolfram Alpha?
Yeah, I have used it.
Is Chirag there today? I can't see the participants here. Chirag is not there. Okay, someone else. Bikash, have you seen this website? Bikash,
Yes, sir.
you have used this website?
Yes, sir.
Okay, maybe one more person. Mamta?
No, sir.
No? Okay, so it's quite useful. Okay, you can, just write integral of something, derivative of something, plot this graph, etc. It will do a good job. So I was curious, so I just did integral gamma. Of course, I don't think complex contour integrals it will do. So you have to convert it to real integrals. But convert it, it's only a circle. So 0 to 2 pi, 1 by 2 pi something. So I was going for the coefficient of z cube. So that's why this 3x etc. is coming. So I did that and it calculates. It is this and this is exactly 7 by 360. Just for fun. But the point of my putting this here is work with a lot of examples. Okay, so 1 by sine z was an easy enough example. Most basic functions you cook up, take nice holomorphic functions, cook up by dividing or whatever, cook up nice meromorphic functions and be comfortable with a lot of basic functions. Because what I might do is because it's online exam etc. I would like to get new questions. I don't want standard questions in some of the exams. We may have real exams with time limit. And for example, if I feel like it, I might give you this kind of an integral for you to calculate. Right? And there's no way you are calculating the integral directly, especially under restricted time. So if you have worked with enough examples, you may be able to venture a guess. This may be the point. It may be coming as a coefficient of, a Lorentz series, whatever. And you will be able to, write down the answer. For example, 1 by sine z, you can easily write down the Lorentz series. The coefficient is 7 by 360. And it's not so obvious that this is related to that integral, but if you have enough experience working with basic functions, whatever function I take, of course, I will take only one of the standard functions, and you will be able to guess what this function could be. Once you make the guess, of course, you can verify. and you would have computed the integral. Okay, so from I don't know how useful these things are in complex analysis, but certainly for the purpose of my exams, doing these things will be useful. Okay, so work with a lot of examples. I might ask you to compute a complicated looking real integral, and there's no way you are integrating because that wouldn't be easy. Right? This kind of an integral, I have no idea. How does one do it? I mean, even if one does, it may be slightly complicated. In fact, I don't know. I mean, maybe one of you can tell me, a computational engine like Wolfram Alpha, how do they do these integrals? Suppose, I just type this and I got the answer. I have no idea how they do it, right? Will they actually do a real integral, so some approximation, numerical approximation to the real integral, or would they be doing what I have in mind? Would they do the
Wolfram Alpha. For some basic stuff, it is actually quite a smart engine. So
Yeah. So do
it
you?
can do indefinite integrals also.
Yes, I know. Yeah.
So
But
for some things it could do this.
yeah,
For some things, I guess it could just do some approximation.
yeah, but my question is, this is a real integral that I have given, right? So will they do some kind of approximation to the real integral? I mean, okay, my question is there a way that they are seeing what we are thinking? It is a coefficient of 1 by sine z Lorentz series expansion, and therefore the answer is this. They may not be able to do that, right?
It might be able to. I mean, I wouldn't be surprised if it is doing that because it does. It does
Human,
know complex and all.
that is true, but once I give you something, we are making a guess, right? Probably, see, I have given a particular integral. Now that this is associated to that function, I thought only humans can think like that. Because so what, in order to do this mechanically, what do you need? You need, of course, your data bank will have, all the series expansions of most of the basic functions. You will go back and check whether it is one of those. But you may
Not
have
sure.
you may have so many functions, thousands of such functions, and given any integral, one will go through that in some order and check it. That I don't know. I mean, maybe many. I have absolutely no idea of computation. So yeah. So, but anyway, I mean, if they are actually doing some numerical approximation to the real integral, I'm happier because then only I am actually verifying it, right? Because if they did it the same way, then I'm not verifying anything. So okay, so take many examples and do this. Anyway, it's fun, Even if we know this is the answer, I really, I mean, there was a smile on my face when I saw that this is C. I did not know this is 7 by 360. So I again, opened another window and did 7 by 360 on a calculator, and it's matching to these many digits nicely. So in fact, 7 by 360. So maybe this is the exact answer, right? It may be repeating after that or something. I don't know. So yeah, no, it's fun. So just for fun, certainly you should do such things. I also believe mathematics also we should kind of think of it also as an experimental science, and these are the kind of experiments that we can run or we can do. Yeah, okay. So let's come back to Roche's theorem because for some purpose I was looking at Conway. Otherwise, for this course I'm only looking at Rodin. Though I have taught from Conway long back, I mean, when many years pass, you forget the details. So I have forgotten what exactly Conway had done. So for some purpose, I looked at Conway and I noticed Conway is doing this stronger form of Roche's theorem, and his proof is also different. And in fact, it's a better proof in some sense. It doesn't use any homotopy or anything. It's much more elementary. So I thought I'll just take your attention to that. I think all of you have Conway also the book. Have a look. It has certain things written differently. So I was checking Conway's book and I thought we should mention Roche's theorem for a meromorphic. Yeah, so this is another point. For holomorphic functions we did, but you can do for a meromorphic function also because argument principle we have done for a holomorphic function, we have done it for a meromorphic function. You will get number of zeros minus number of poles. So what should be the statement of Roche's theorem for a meromorphic function? If f and g satisfy that strict inequality as hypothesis on gamma star, then instead of saying number of zeros equal to number of zeros of f and g, you will get number of zeros minus number of poles of F equal to number of zeros minus number of poles of G. So, it may have good uses of this particular formulation. So for metamorphic also we can state, and that's what Conway has done. So you can guess the statement. If you have the strict inequality on gamma, okay, in our notation on gamma star, I used to write, I think, so on gamma star, then inside gamma, so I'm putting inside in quotation marks because of Aryaman's comment in the last lecture. He asked whether I'm using Jordan curve theorem, etc. I'm not. So inside us, just from what we visualize, anyway, usually it's a circle or something, so inside us well defined. And so the strict meaning of insiders, as we discussed in the last lecture, you take those points where the index is 1. And there you are counting the zeros. So here we will be counting number of zeros minus number of poles. And of F and G it should coincide. And our proof goes through. Right? Our proof. So I think last time we had this discussion. So I said that assume Fs, right, when we were stating the weaker version of Roche's theorem, I said that assume that F does not vanish on gamma star. And then on WhatsApp, Aryaman asked this question, why do you need to assume? Doesn't it follow from the strict inequality? And I agreed with him, and I think so. I agree with him even now. But I also see that all the places, they do state it like this. Even Conway states that assume neither F nor G has a pole or a zero. That's part of the statement. Anyway, let's not bother too much because we know that that condition has to be there, and it does follow from the inequality, certainly for zero. But maybe, for interpreting it for a pole that it follows is not. Right, for a zero it follows, because if both of them are zero, then you will get zero strictly less than zero, which is not allowed. One of them is zero, then you will get mod f strictly less than mod f, which is not allowed. But on a pole, you will get something like infinity strictly less than infinity. So I'm not sure, whether it's allowed or not allowed. Anyway, doesn't matter. Assume it does not have a pole on gamma star. Assume, if you want, it does not have a zero also on gamma star, or conclude it from this hypothesis. Anyway, these assumptions should be there. Either you conclude it or you assume it. That's not the main point. And then our proof will go through, because we compare the index of F composed gamma at 0 and index of G composed gamma at 0. So F composed gamma should be a curve. Now probably there are poles around, but if you assume that F has no pole on gamma, then F composed gamma is a closed path. Right? It is a path. It is piecewise continuously differentiable, because on gamma F is holomorphic. Though F is metamorphic everywhere, on gamma, meaning take any point on gamma star, and a small neighborhood F is holomorphic. So F composed gamma remains a closed path. Similarly, G composed gamma, and the index at 0 over F composed gamma is same as the integral of F prime by F was a one variable calculus computation. So that of course goes through, and that integral, now argument principle for metamorphic function would say is number of zeros minus number of poles. And F composed gamma index at 0 and G composed gamma index at 0, they are the same because the same homotopy works, straight line homotopy. So F composed gamma and G composed gamma are homotopic in a domain that does not contain 0. Does not contain 0, because if one of the homotopy maps go through 0, you will get a contradiction to the strict inequality. So the proof goes through, and we have proved actually this stronger statement. So these things make sense, right? Because F has no 0 on gamma star, the index is well defined. Similarly, this index is well defined, and they make sense, and they are equal by straight line homotopy. So our proof also goes through, but check the proof in Conway. That's I think much more elementary. So what Conway does, so I did not write it down. I didn't have enough time to copy paste the thing. So you check it, but anyway, verbally, let me tell you. You have the strict inequality, divide throughout by mod G. When you divide throughout by mod G, what do you get? You will get mod of F by G minus 1 is strictly less than mod of F by G plus 1. From that, you can conclude that F by G cannot be a negative real number, right? Because this is what we used in order to show that homotopic, those paths will not go through 0. Same argument. If F by G is a negative real number, you will get some number strictly less than the same number. So you conclude from the strict inequality that f by g, f and g are meromorphic, so f by g is meromorphic, and this meromorphic function f by g will not take values in the negative real axis. So the range is, the codomain of f by g is c minus the negative real axis, complex plane minus the negative real axis. Now you might remember branch cut, etc. So if you remove this negative real axis, you have a branch of the logarithm, right? In fact, what we call the principal branch, because you are removing the negative real axis. So you have the branch of the holomorphic branch of the logarithm. And what is f prime by f? It is the derivative of log f. It's a logarithmic derivative. So if you have f by g, then log f by g you can take, and its derivative is nothing but f by g prime divided by f by g, and that you can check is nothing but f prime by f minus g prime by g. Okay, so what you are saying is the integral of that we are considering is integral of f prime by f by g prime divided by f by g, that has a primitive. It is nothing but log of f by g, where log is holomorphic because you are not on the negative real axis. So because it has a primitive, the integral is 0. That's it. And you would have proved Roche's theorem. In fact, the stronger version of Roche's theorem, that's another proof. In fact, in the meromorphic setting. Okay, so it is quite a distinct proof. I don't think it's using anything that we have used. It's only using that there's a holomorphic branch of the logarithm. But if your branch cut is so nice, like a whole half axis, then saying that it has a branch is elementary. You don't need any homotopy or simply connected or anything, right? You can by hand you can construct a branch on such a nice branch cut. So it's quite an elementary proof. Okay, so anyway, check it.
So the thing in the previous slide,
Yeah.
so after dividing by g, we got that f by g can never be a negative real.
Yes.
But that was on gamma star, right?
Okay, right. So that was on. That's correct. Yeah. 5G. Yeah, because this strict inequality is only on gamma star, right?
Yeah.
You're right. So f by g, we are ruling it out on gamma star. Yes, that is true, and that's okay because even in our homotopy proof, we are ruling out that 0 is not there on gamma. Yeah, so there it was okay. You're ruling out on gamma star. So here, what do we need to show? We need to show that yeah, here also, only on gamma star will matter for the argument. So please check the proof in Conway. But if you can visualize the, whatever I'm saying verbally, what do we need to show? We need to show that the integral over gamma of this function, right? Let's call f by g to be p. Okay. So integral over gamma of p prime by p is what we are interested in, right?
Yeah.
So we only need to know, and it's one variable calculus after substituting for gamma.
Yeah.
Assume that gamma has a parameter. Of course, gamma has a parameterization, and then we are dealing with one variable calculus. So you need to know this thing only on gamma, no? Because
Okay. Yeah. Yeah.
right, because integral is over gamma, so it will be integral over a to b or 0 to 1 f of gamma of s by phi of gamma of s by something. So this information, but good that you asked. I also got confused for a moment. So this information you need to know. So f is considered for this argument. F is considered as a function on gamma star only, because the curve is f composed gamma even in that argument. So that's enough. It's okay, no, Ariman?
Yeah. Yeah.
Look okay, but double check. Anyway, look at Conway. This is the argument, and it goes through. So it's the same idea that we are using, but I feel this is slightly better, right? What do you think? Because you're only using a standard branch cut, therefore constructing the holomorphic branch had no real thing in it. No, it's by hand, right? See, if your branch curve was some funny curve, of course you need theory in order to construct a holomorphic branch. Then you would have used homotopy, etc. But because it's a plain half axis that you are removing in 105 calculus itself, you would have done that kind of a problem. So that's very elementary. And then it has a primitive. But it has a primitive. It has a primitive is using. How does one show something as a primitive? It is using Cauchy theorem, but only Cauchy theorem for a triangle, nothing more. So this is a bit more basic than our proof, more elementary than our proof. Well, our proof is also elementary, but it introduced this concept of two curves being homotopic. Once that concept is there, then that is also elementary. But I still feel this is slightly better. Oh, by the way, it is rare for see, compared to many other disciplines, many other subjects, right? If you are doing physics or biology, certainly, or chemistry, I think by this level, when one teaches an elective, I don't know, I'm assuming, from whatever I hear from colleagues and others, or what one reads on popular magazines, an elective in any other subject other than mathematics, I guess, will have many modern things as part of the syllabus, right? I can easily visualize, in biology or chemistry or even in physics, if you have an elective, advanced topic, it will involve a lot of new things and the syllabus will change, etc. Whereas that's not the case in mathematics in general. No, we will still be doing classical things because we have to, do 19th century stuff, even at this advanced level or early 20th century stuff, typically in an elective. But what I've noticed when I was preparing these slides is, at least, history of mathematics wise, we are getting some new things. For example, we did global Cauchy theorem. The proof that we did is 1971. And Rouché's theorem, though Rouchet died in 1910, so exactly I don't know when Rouché's theorem came. It was certainly before 1910, before his death. But we had this historical comment there also, right? We had this historical comment that the stronger version, though it's as easy as the other version, but it has to click. No, somebody has to think about it, and ideas can take time. And we said that certainly it appears in 1962 in a book in 1962, and therefore it's certainly before 1962. But 1962, 1971, all these are modern from the point of view of mathematics. At this level, because we are dealing with Weierstrass and Cauchy and all our, people from generations ago. So historically, we got 1962 some remark, 1971 one remark, and when I was looking at this proof in Conway attributes a stronger version, this version, to 1976. And there's an article in American Mathematical Monthly in 1976 by a mathematician called his first name is Irwin and last name is, I think, Glicksberg. I forget Glickberg or Glicksberg. Glicksberg, I think. Glicksberg. He's a famous mathematician, but I'm not from this area, so I don't know these names. But when I checked about him, he is quite a famous mathematician, Irwin Glicksberg. And he had this popular article in American Mathematical Monthly where he actually proves. So he did not know this stronger version, that it was there. So he gets a stronger version on his own and he gives a complicated proof, I think. I did not check the original article, but it's not this easy proof in Conway. So easy proof in Conway may be Conway's proof. I don't know. He doesn't refer to anything else. But Conway does make this historical comment. Am I taking too much time? No, I have time. Conway makes this historical comment that the stronger version is due to Glicksberg and it is 1976. So there is something called MathSciNet. How many people know about MathSciNet? There is American Mathematical Society and they have this mathematical reviews and it is also there online and that is called MathSciNet. So you can search for math papers online and each math paper will have a small review by another mathematician. So mostly even if you cannot access a paper, if you can access MathSciNet, you can get what is the main theorem of that paper, etc. How many of you know about MathSciNet?
I
Mathematical.
There's a link on it on the math webs on the
Have you,
ITD math website.
have you ever clicked it?
Yeah,
So
but
you
I
know it.
think outside I think it requires the ITD internet to access it.
Yeah, because we are paying for it, so it's IITD consortium. So you need it, but what one can do, but right now you can't do it because you're not here. But when I am here, if I enable, so there is a way to enable offline access, but you have to be at a place where online access is there, which via VPN also you can get. You can, log into IIT network via VPN. I don't know how to do it, but others do it. Certainly, you should be able to do it. Anyway, you don't need MathSciNet now, but if you are interested, and once you have IIT network and once you log into MathSciNet, there is what is called click offline access. So 90 days it will be valid. So you have to be in IIT once in 90 days in order to have access. Yeah, so I checked for this particular American Math Monthly paper, Blitzberg and MathSciNet, and its review says, here is this new proof, etc. And then there's an update of the review. And the reviewer, whose name I forget, says that some other mathematician whose name is there, I forget, has informed me that this particular stronger version of the theorem is already known, and it is already mentioned in the 1962 book by, what was his name, Theodore Esterman. So this information is, so it's so I got this info from Wikipedia. So Wikipedia is so good, I mean, even on such such esoteric matters, Wikipedia is pretty up to date. So this 1962 reference was not all that famous, but Wikipedia has it. Okay, so I mean, we are getting some chance to talk about some modern years, 76, 62, and 71, various scholars. So that's good. Yeah. So this is also from Conway. So many standard results can also be proved via Roche's theorem. So I like this proof. So this is page 126 of Conway. So fundamental theorem of algebra, here is another proof. By the way, most of these things we can use Roche because there's no circularity. Because for Roche we haven't used many things. Certainly we are not using fundamental theorem of algebra to prove Roche. So what do you need to show? Here is a polynomial. You have to say it has roots. In some sense, this proof is slightly better also, or at least it gives a feeling that it's better. I don't know whether it's really better or not. We will see. Let's discuss. Yeah, so you have this polynomial, and what do you need to show? It has at least one root, right? How many of you have seen this proof using Roche's theorem, proof of FTA? Ariman, have you seen this proof?
I saw it.
You
Yeah,
saw
I
it?
saw it like the day before only. Yeah.
Where? In Conway?
No, I think on Wikipedia.
Wikipedia, but the Wikipedia article not for Roche's theorem, but for fundamental theorem of algebra.
No, I think I was looking at Russia only because I wanted to see what
No,
the zero thing was
current
there.
times, I did not notice. Yeah, I did not read everything. I just went through quickly. But anyway, so yesterday I noticed it in Conway, and then I remembered I had seen this long back in Conway because once I taught this course using Conway, so at that time I must have done this, but I had completely forgotten. So yesterday when I saw it, it looked like new to me. Uh, so consider this limit, and easily from this you can check that this limit is 1. So for every epsilon, there is some number such that mod z bigger than m. You can make that difference less than 1. In particular, take epsilon to be 1 and choose such an r. Therefore, for mod z bigger than r, this difference, right, pz by z power n minus 1, this modulus can be made less than 1. My epsilon is 1. So mod z bigger than or equal to r implies modulus of pz by z power n minus 1 is less than 1. Clearing the denominators, pz minus z power n is less than mod z power n. Now apply Roche to mod z equal to r. On mod z equal to r also this is true, and f minus g is strictly less than mod f. So f and g should have the same number of zeros in the disk 0, d0, r. And z power n of course has n roots. Therefore p has n roots. So beautiful proof, very nice proof. And let's discuss. Some of you make one or two comments. I would like to say, or quickly, I get this feel. I mean, my first feeling is this is slightly a better proof because not only that it has n roots, but it is saying that it has n roots in this disk itself. Is that better than our previous proof? Our previous proof also we had some control, no? Because not only that we showed that beyond a stage our argument goes through, but we also had it in terms of the coefficients, no? Which I gave as an assignment question. So there also we had some control, but this looks like a better control, but I did not really check that. Right? If you had some proof, then it will only say that it has n roots. But the proof that we had given, we did something constructive and we had some control using the coefficients. And here also you are getting in some disk. So what exactly this R is, maybe coefficient information only is coming in. But exactly what is the coefficient? So, some of you please check this. What exactly can you conclude about this R in terms of the coefficients and compare with our previous proof? So let me leave it as an open assignment. Okay. If you're interested, check it. There is something to be checked. Maybe you are getting something better. That's my feeling. I could be wrong.
And then here also we can choose some R constructively, like
That's what I'm saying.
1
So
plus mod A naught plus.
correct. Correct. So what I'm trying to say and what I'm asking you to check is this R constructively that you will choose. Are you going to get a better R than the R that we have chosen? That's my. So that needs a checking. No, that checking I haven't done. Is what I'm trying to say is clear, Ariman?
Yeah, yeah.
You get a constructive R, and that R, of course, should involve the coefficients. But are we getting a better construction than the previous one? Then I will say this is a better proof. Otherwise, but still, I like this proof because that proof used that particular identity, Parseval's or whatever. And I like Rouché's theorem. So wherever Rouchet is used, I like it. Okay, so this is FTA, and there's also this open mapping theorem via Rouchet. So this is also there in many books, but since I haven't seen the book itself, I saw a screenshot of the book at this link, so I thought I'll refer to this. But it's also from a book, and that book is referred there. I forget the authors. So what do we need to show? If you have an open set in your region, Fs holomorphic, Fs non-constant. I will not write it always. Fs non-constant. You have to show that f of v is open. So you have to show that f of v is open. So take a point A arbitrarily, and then therefore f of a is an f of v, and you have to show that there's a small neighborhood of f of a which is completely contained in v. And how did we prove this? We see up to now we have not used open mapping theorem in whatever else we have done. We proved open mapping theorem and then we did other things and then we did Rouchet. So there's no circularity here also. Right? Rouchet is using argument principle, which is using residue theorem, which is using global Cauchy. None of that uses open mapping theorem. So there's no argument. There's a different proof therefore. And take A and V. And therefore you have f of a. It's very similar. So you will write f of z minus f of a as z minus a power m times gz, right? If m is the multiplicity, and gz has the property that there's some neighborhood of a where g is of course holomorphic everywhere, and on some neighborhood of a g is non-vanishing because m is the multiplicity. This was used earlier also, and there in that proof we use the fact that g is non-vanishing, and I think we considered g prime by g, and maybe we use the inverse function theorem on that thing, and we somehow we wrote it as exponential of something and use that exponential information to take an mth root. So we took an mth root of this function in a nice fashion. That function phi was holomorphic and had all the nice properties. That was the argument. That was also a simple enough argument, but this is Rouchet. It's nice. So what we will do is these holomorphic and non-vanishing on a small disk. In fact, you can choose the disk to be by taking R even smaller. You can take the disk to be the closed disk, which is important because I'm going to use the compactness. Because it's compact, mod fz minus fa will take a minimum there and call that delta. And this delta is positive because it does. Yeah, why is this delta positive? Why is the minimum not 0 on this compact set, on this circle? Because on this circle, fz minus fa is never 0, right? Because g is never 0 on this closed disk and in particular on that circle, and z minus a is not 0 anyway on the circle. Circle is mod z minus a equal to 1. So delta is positive because it's compact, it will attain a minimum and that is positive. So you got a delta which is a positive number. So delta is positive. And we are going to claim that this particular delta neighborhood of f of a is completely contained in f of v, and therefore f of v is open. So that's it. Precisely you are getting a particular neighborhood which is completely contained in f of v. And what is the argument here? That is Roche's theorem. So indeed, if you take a beta in this, you have to show that beta belongs to f of v. But beta belongs to f of v means f of z equal to beta for some z, meaning fz minus beta has a 0. So you have to show that the function fz minus the constant function beta has a 0, and we are going to show that it has m zeros by Roche's theorem. You just need to show that it has 1 0. So if you take this function fz minus fa minus this function fz minus beta, so this is my f and this is my g in Roche's theorem. So what is this difference? Fz goes away, so this is beta minus fa. So this is modulus of fa minus beta, and fa minus beta, beta is from this disk. So fa minus beta is strictly less than delta, and delta is less than or equal to mod fz minus fa, because delta is a minimum on this disk. On this disk, on mod z minus a equal to r, delta is less than or equal to fz minus fa, because delta is the minimum. So you have got modulus of f minus g is strictly less than, here it is strictly less. So strictly less than modulus of f, right? Modulus of some function minus another function is strictly less than modulus of this function. Therefore, on the boundary, on mod z minus a equal to r, therefore in the disk dA comma r, in the disk dA comma r, this function and this function will have the same number of zeros. But this function has m many zeros, exactly m zeros. And therefore this function has exactly m zeros. You just wanted to show that it has at least 1 0, so you are done. So again, a nice proof. So yeah. So earlier proof, the main ingredient was the minimum modulus theorem, and here we are using Roche's theorem. Why was the main ingredient minimum modulus theorem? Because we proved the inverse to what I call towards OMT, which was basically inverse function theorem plus a little bit more, and that the main idea was minimum modulus theorem, and that we used in the proof of extracting an mth root of g with nice properties. Right, this function g, we extracted an mth root, and that mth root had nice properties, and there we had used the previous result, which used the minimum modulus theorem. So this is another proof. This also says it has m roots, etc. So it's nice. Okay, so I think it's time to stop. So we will continue more informal conversation if you have things to discuss. Otherwise, we'll end earlier than usual. So let me stop this recording. Stop sharing the screen. Yeah. Attendance is not bad. So I have this feeling that these online classes have more attendance than the offline classes that we used to have. Is that your feeling from all your courses? Yeah, let me also stop recording before all this informal chat. Yeah.